Right, optimization, which is pretty much the reason why we need to learn differentiation in economics. So what is optimization? Optimization is the process of finding the maximum or minimum of a function. Why would you need to do that? Because in economics, what we study involves utility maximization and profit maximization. Pretty much all the mathematical theories that you're going to come across as an undergraduate in economics would involve some sort of optimization. Now let's go think about how we approach this problem without calculus. In high school, if you learn economics in high school, or if you take basic microeconomics, sometimes it is taught without calculus. So what do you do in those cases? You're still studying human behavior that involves making choices. What do we do in those cases? If you remember, when we talk about utility maximization in a course without calculus, what you do is you have to be given marginal utility, right? It's something that you are given. So suppose the utility function is log x, then the marginal utility is something. Find the optimal consumption for this consumer. You're given marginal utility. In the case of profit maximization, you will usually be given marginal revenue and marginal cost. And then the profit maximization point is given by MR equals MC. So you're given all these information so that you can compute the optimal point without calculus. So where do these information come from? How do you find marginal utility, marginal revenue, and marginal cost to begin with? So where do they come from? They come from, well, let's think about what they are. They are the rate of change of utility function, revenue function, and cost function respectively. So they are rate of change. In other words, they are derivatives. They come from differentiation. When a teacher, like me, write a question for students without calculus, what I did was to take the derivative, figure out what the marginal utility or marginal revenue should be, and type it in to the question for the student. So in an economics course without calculus, the differentiation part has been done for you by the teacher. That's what happened. So there is no way of avoiding calculus. It's just a matter of who does the calculus. In a course without calculus, then the teacher would have to do it for you. But in more advanced courses, like in intermediate microeconomics, you would need to do the differentiation yourself. So you will no longer be given marginal utility and marginal revenue and marginal cost. Those are functions that you have to find. You have to find yourself. So let's proceed in thinking about how we find such quantities. Let's start with maximum. What is a maximum? Like, okay, so this is like, let's say this is function fx. What is maximum? Well, maximum is the point that's at the very top, right? Okay. So that's where the maximum is. How do you find that point? To understand how we find that point, we want to think about what properties you have that we can observe from this diagram. What properties can we observe from this diagram? Let's see. Let's look at the shape of the diagram. This is the maximum. If you look at the shape of the diagram, what's happening? The function is going up before it reaches the maximum point, and then it goes back down. right? That's the point. That's the definition of a maximum. Maximum has to be higher than the points around it, right? That's the meaning of a maximum. So that means that all the points around the maximum has to be lower than the maximum. And the only way you can achieve that is for the points to be increasing as x increases, and then once it reaches the maximum, well, the function has to start decreasing. That's the only way that the maximum could be actually a maximum. So the function is increasing on the left and decreasing on the right. What does that tell us about the slope? And if a function is increasing, by definition, its slope is increasing. Its slope is positive. If a function is decreasing, by definition, its slope is negative. So that's what we observe from this diagram. If you have a maximum at a certain point, then the slope must be positive on the left-hand side of that point, and the slope must be negative on the right-hand side of that point. That has to be true. What happens at exactly the point of maximum here? What's the slope at that point? Well, if the slope is positive on one side and the slope is negative on the other side, then naturally, as you can see from the diagram, the slope should be 0 at the maximum. So that's what we observe from this diagram. For any maximum you can think of, the slope should be positive on one side, negative on the other side, and the slope should be exactly 0. Now clearly, this only applies to function that is differentiable, or at the minimum it has to be continuous, because otherwise you won't have this shape. The way I draw it is essentially a quadratic function, which is a polynomial. So if for a polynomial this logic holds, but if you have functions that look like that, it might be different. In economics, we as I've mentioned before, almost all the functions you see will be continuous and differentiable, because the math would be a lot easier that way. So we're going to ignore these cases now. We're just going to focus on cases where we can use differentiation, and polynomials are one of them. They will look like this: maximum, increasing slope, decreasing slope, and slope is 0 at the point of the maximum. What about minimum? Once again, that's a very typical minimum. Here's the minimum. How do you find this point? Let's take a look at the properties around this point. A point is a minimum if it's lower than all the points around it. So how do you achieve that? You achieve that you can only achieve that if the function is decreasing on the left-hand side and increasing on the right-hand side. That means the slope is smaller than 0 on the left-hand side, and the slope is larger than 0 on the right-hand side. At the point of the minimum, the slope should be 0, because you're switching from a negative slope to a positive slope. So the slope is 0 at that point. Right. So that's what we observe from drawing diagrams of maximum and minimum. It turns out that in both cases, the slope would be 0 at the point of at the point of maximum or minimum. So finding maxima and minima would involve finding all the points where the slope is 0. There might be more than one. There's nothing that says that you only have one single maximum or minimum. You could have diagrams that look like that. In that case, you have multiple points of maximum and minimum. That could be maximum and minimum, right? So these all would have slope equals 0. That could happen, and it's your job to verify that which one is actually the real maximum. That's because the process of taking the derivative of a function that gives you the slope, and then you setting it to 0 to find all the points at which the slope equals 0 only gives you what we call a local maximum or local minimum. Let's take a look at this example. Let me draw it less swift. Okay. All right. Yeah, that's better. Okay. Take a look at this function. It's a very weird shaped function, and if you let's say I give you the equation for this function, and you take the derivative to find the slope, the function for the slope, and then you set it to 0 to solve for all the points that gives you potential candidates for maximum and minimum. What would you find? That's what you find. Okay. All right. In this particular function, there are actually a lot of points. Okay. You can see that the points, the fact that a point is higher than all the points around it does not guarantee that it's going to be higher than all the points on the function, right? This point here is not it's certainly not the biggest, right? Because you have so this point is certainly not the biggest because you have a point that is even higher than it somewhere else. The process of setting the slope equals 0 only gives you only gives you what we call local maximum and minimum. The points are the biggest around a neighborhood of points. So you can see that, well, it's true that this point is a maximum in the sense that it's higher than all the points around it. It's just not higher than all the points on the curve. Similarly, there's no guarantee that this point on the left is actually the global maximum because you don't know what happens beyond the parts beyond the area, the region that I draw the curve. In general, if you have a function that is if you have a function that has the real number line as its domain, well, you have to make additional assumptions in order for you to know which point is the global maximum. This process of taking the derivative and setting to 0 only tells you, well, this point is higher than all the points around it, but there's no guarantee that it's going to be higher than every single point on the curve. Similarly, for minimum, there's no guarantee that a particular point is going to be the lowest on the whole function. It's just that it's lower than other points around it. So, okay, so we have a local minimum, local maximum, local maximum. Now, in this particular case, you can see that the local minimum is certainly not the smallest because the function is going lower than this point on the right-hand side. Right, so we have local minimum, local maximum. There's one more point that's very special here. This point. This point, is it a minimum or maximum? This point is actually neither. The function is going up on the left, becomes flat, and then going up again on the right. So it's not a maximum, nor it's a minimum. This is called an inflection point. It's called an inflection point. And it's usually not something that we are interested in. So we want to eliminate these cases. So inflection point. These are cases where you have a flat slope, but they are neither maximum nor minimum. So we're not interested in these cases usually. But then this process of taking the derivative, setting the derivative to 0 to solve for x would give you all these points, and you have to sort them out. So how do you sort them out? That's where you need to go back to the diagram we drew just now. To know whether a point is a maximum, minimum, or neither, you need to know the rate of change of the slope. Right? So max, mean, neither. Maximum, as we have already mentioned, would look like that. The slope is going from positive to negative, so slope is decreasing. For minimum, the function is going from decreasing to increasing, so slope is increasing. And for inflection point, slope is flat, it's not changing. So that's how we figure out, is the slope increasing, slope is decreasing, or is it flat? That would tell us whether it's a maximum, minimum, or neither. And that's how you do it. You have to find the rate of change of the slope, which means you have to take the derivative again. You take a derivative again. You're taking now the slope itself is already a derivative. So you're taking derivative again, and that's called second derivative. It's usually denoted by f prime prime x of d squared dx squared fx. So they mean the same thing. That means that you are taking derivative twice. When you take the derivative of a function, you get another function. Since it is a function, you can take the derivative again. You can actually take it many times. It's just that in economics, we typically do not need more than second derivative. So now that we know the idea of second derivative, once again, what would we expect? Maximum, slope is decreasing, right? So what you would expect is ddx slope would be negative. For minimum, the slope is increasing because the function is going from a negative slope to a positive slope. So ddx slope would be positive. And if it's neither, then ddx slope would equal to 0. That's it. You just have to do the derivative, take the derivative again, and depending on whether you are looking for maximum, as in profit maximization, or looking for minimum, as in cost minimization, you look for the points that satisfy the requirement on the slope. All right, example. So now we're going to use some very common example. Let's say John's utility function is u x w equals to 5x plus w. Now, in this function, we have two arguments. Where x is number of oranges and w is wealth, right? So that's a very typical economic application. You have a utility function that depends on money and some product that the individual can buy. And he cares about money and he cares about whatever he is buying. So with initial wealth is $500. He has $500, and cost of oranges equals to x squared. These are very expensive oranges. They get more expensive as you buy more. That's just to make the problem easy to solve. Right, so how do you solve this problem? This is a very typical utility maximization problem. If John buys X oranges, his wealth equals to 500 minus X squared. Utility equals to ux 500 minus x squared, that is 5x plus 500 minus x squared. That's the utility function. Okay, how does it look like? Before we proceed, let's see how it looks like. This function looks like this. It's essentially, it's quadratic. And because it's quadratic, that means that you should be able to find a point that gives John the highest utility. That's actually one of the reasons why you would like to use quadratic equation as utility function, is that there is one single point at which it's maximized for all the ones that looks like this, right? Quadratic function goes up, and down. So you know there's one single point, and it is the global maximum. It is the global maximum. right? So we're going to take the derivative of the utility. In this, or I can just use ux if you want. So we're going to take the derivative of utility. And that's the derivative of 5x plus 500 minus x squared. And we have to set it to 0. And solve for x. That would give us this point in the red dot. So that's what we're looking for. This point. d dx 5x plus 500 minus x squared has to equal to 0. Now what you're going to do technically is you're going to use the sum rule to split the sum into different derivatives, and then you're going to use the constant multiple rule, derivative of a constant, and then a power rule respectively. But as I said, there's no need to explain what you're doing with something this simple. You just directly write the answer, which is 5, because the derivative of 5x is 5 times the derivative of x, which is just 1, so you have 5, plus 500 goes away because the derivative of 500 is 0, minus power rule 2x to the power 1, so just 2x equals to 0, so x equals to 2.5. That means John is going to buy 2.5 oranges. However, we haven't actually verified that this is a maximum. It could be a minimum. We have drawn the diagram so that we know. But in an exam, you're probably not going to draw a diagram every single time, and the function is usually not going to be this simple that you can draw easily. So we might not be able to draw a diagram, so you won't know that this is actually a maximum until you verify that the slope of the slope is actually negative. So now you have to take the derivative of the slope. That's the second derivative. That's the second derivative of our utility function, 5x plus 500 minus x squared, which is also equals to the derivative of 5 minus 2x. So that's what we're going to do. Take the derivative of 5 minus 2x, and once again, what you're doing is using a sum rule, then the the derivative of a constant, then the multiple rule, and so on. What you get is negative 2, which is smaller than 0. So to conclude, x equals to 2.5 actually maximize utility. And therefore, John will buy 2.5 oranges. Okay, so that's the answer. That's a very typical economic question in consumer choice. You will be given a utility function, prices, wealth, and then you'll be asked to figure out how many units the consumer will buy. And this is what we just do. The process that we go through involves 2 steps, right? It involves first taking the derivative of the utility function in order to figure out how many units to buy, and then you take the derivative again to figure out whether the quantities that you have found actually represent a maximum or not. We have names for this process. When you take derivative of a function and set it to 0, it's called first order condition. Or usually just FOC for short. So this is this process, taking derivative and setting to 0. The second part involves taking derivative of the slope, and that's usually called the second order condition. These are just names. Or SOC for short. So these are the process that you have to go through in almost every single optimization problem you will face in the next few years. Take the derivative of, take the derivative of utility function, or in the case of profit maximization, you'll be taking derivative of the profit function. Set it to 0. Solve for x. That gives you candidates for maximum utility or maximum profit. You have to calculate the second order condition and verify that the points are actually utility maximizing or profit maximizing. So there's one more thing I want to mention is, as I mentioned, there are some common functions in economics. Quadratic is one of them. Quadratic is one of them. Why is quadratic attractive? Quadratic is attractive because it has a single maximum, right? That's why it's attractive. It has a single maximum. That's one reason. There's another reason is that the way that it is going up. Let me give you the other ones that are very popular. The other ones that are popular includes natural log. So log is very common. And one more that is very common is the negative exponential function. So these three functions are very common in economics, including financial economics. Why are they so attractive? Why do we keep using them for utility functions and profit functions? Utility functions and profit and production functions. Why they are attractive? Because of the same reason. Look at how they increase. The way they increase, they are increasing slower and slower. That's the common property of all three of them. They're going up and they go up slower and slower and slower. In economics, this is a very important property for theoretical reasons. We think that this is actually a realistic assumption, that utility and production goes up slower and slower. What is that? Is that something you have learned in basic microeconomics? Increase slower and slower. So that's why do we like that property? We like that property because that's diminishing marginal utility. You get less happy as you have more of the same item. That's diminishing marginal utility. And in production, you have diminishing marginal return. As you try to produce more of the same item with the same by increasing a single input, you get less efficient. In both these two cases, diminishing marginal utility and diminishing marginal return, you both have functions that is of this shape. That is the quadratic, log, and negative exponential. They all increase slower and slower and slower. That gives us the property that we think is realistic in economics. So these three functions you see a lot, and very conveniently, they are all differentiable. So it's very easy to find maximum in these cases. You just have to take derivative and set it to 0. So that's why they are very common. All right.